So in section 2.2, we're going to talk about more methods of proof. In section 2.1, we learned how to prove something directly. And we also learned how to find a counterexample to show that a theorem is actually false. It's not really a theorem. And today we're going to learn, well, depending on how far we get today, we're going to learn 5 more proofs, or methods of proof. I'm starting with this one, a proof by contradiction. There's a little bit of a typo here. Not sure it makes sense with the word will, but we can establish an implication. P implies Q by assuming that P is a true statement, a true proposition, while Q is a false proposition. And remember that when P is true and Q is false, the conditional statement as an overall proposition is false when P is true and Q is false. So what we need to do in order to show that this can't be false is to find some sort of contradiction, something that goes wrong. And these usually look something like a statement is both true and false. So something like R and not R. And if maybe you think this is a little strange, we actually, way back in the last chapter, talked about this kind of thing, even though you didn't know it at the time. We actually showed that the conditional proposition, if P then Q, is logically equivalent to the statement, it's not the case that P and not Q. So essentially what we're doing in a proof by contradiction is we're showing that this is a true statement by showing that it's impossible for P to be true and Q to be false at the same time. So we're using some of these properties of logic that we learned in proofs. Are there any questions about that idea before we try to make our own proof here? Okay, so if there aren't any questions, we'll move on. And actually, after I wrote these notes and posted them, I decided to actually do a slightly simpler example here in class. So what I want to do is cross this one off and tell you to take a look at this one in your textbook. Since it's in there. And we're going to do a different one that's a little bit easier to get a grasp on. We're actually going to show this one. For every integer n, if n squared is even, then n itself must be even. Okay, so a proof by contradiction, you still start by writing proof so that whoever's reading this knows what you're doing. And it's also important to tell the reader that you're going to be using this method, that you're going to be using a proof by contradiction, because if you start writing something different than the theorem, if n squared is even and n is even, your reader is going to be left wondering what's going on. So you might say something like, suppose by way of contradiction, or something similar. You could literally just write, we will prove this by contradiction. But I like this. Suppose by way of contradiction, assume that n squared is even. So we're assuming the hypothesis is true. And we also need to assume that the conclusion is false. So in this case, we're assuming that n is not even, which means it's odd. And what we're going to do now is look for some sort of contradiction, something wrong with this statement. And we'll work the same kind of way. We need to next think about the definitions. Maybe we'll start with n being odd. So since n is odd, we know that there's an integer k where n is equal to 2k plus 1. And if we want to get an idea of how n is related to n squared, we could just square both sides of this. So let's do that. So n squared is equal to this side squared, 2k plus 1. And we know how to FOIL things out. So we can work through 2k times 2k is 4k squared. Then we'll get a 2k times 1, and then another 1 times 2k, and then finally a 1 times 1. But this is a little messy. We should probably remember how to collect terms. So combine the two k's, the two 2k's to get 4k. And now we need to decide if we're looking at an odd or an even number. What do you think? Is this odd or even?
Odd.
It's an odd number, right? So if we're going to say it's odd, we need to rearrange it slightly so that it looks like 2 times an integer plus 1. And in order to do that, we'll have to factor a 2 out of both of these expressions here. So this is equal to 2, and then what's left over is 2k squared plus 2k plus 1. So now we've shown that n squared is odd. So let's say that. Because this is a problem. Remember back at the beginning, we assumed that n squared is even while n was odd. So this contradicts what we assumed. And since a number can't be both odd and even, that means we have the contradiction that we were looking for. So this is where we stop. Are there any questions over this example of proof by contradiction? Okay, so since there aren't any questions, we'll move along to the next kind of proof. Proof by contrapositive. And it looks like I mangled my sentence again. Several mistakes slipped into this set of notes. This should say, we saw it in chapter 1. Looks like I was trying to write two different sentences at the same time. We saw in chapter 1 that the conditional statement, so we're still talking about conditionals, if P then Q, is logically equivalent to this statement, not Q, then not P. And this is what we called back then the contrapositive. So sometimes when you're proving something, it's easier to prove the contrapositive of a conditional than it is the original conditional. So this example is somewhat like the last one that we saw. We have some statement about a number squared, then something about the number itself. The problem with conditionals like this is that if we started at this point with x squared, then we would have to somehow take a square root in order to talk about the number itself. But as you know from algebra, taking square roots can sometimes make things more challenging. So it's better, or at least easier, to start here with x and then multiply it by itself to get x squared. That's much easier than trying to take a square root. So we're going to turn things around. We're going to start with the negation of the conclusion, not Q, and then try to show, not P, the negation of the hypothesis. Okay. So for this proof, we want to be really clear, again, what we're doing. We're going to prove the contrapositive, so let's just come out and say that. And maybe we can even write out what the contrapositive is in this case. So we start with the negation of this part, then x is irrational. If x is not irrational, that means it is rational. So that's how the contrapositive starts. If x is rational, Then we look at the beginning of the old way. X squared is irrational, and we find the negation of that. So that would be x squared is rational, not irrational. So instead of proving the original, we're actually going to show this, the contrapositive. So that means we need to assume this part. We need to assume that x is rational. And then we need to show that x squared is also rational. Does anyone remember what a rational number is?
A fraction?
A fraction, good. So since x is rational, we need to say what that means. It means there are two integers let's call them a and b. Such that x is the fraction a over b. Okay, so since we have x itself, we can simply multiply it by itself to get x squared. So let's do that. So therefore, x squared is equal to a over b squared. And how do we square a fraction? Can someone remind me? Well, the top and the bottom get squared, don't they? So it's a squared over b squared. Are we looking at a rational number? Yes, we're looking at another fraction. A squared is an integer, b squared is an integer. So we just need to state that. And that's it. That was the conclusion that we were trying to reach. Are there any questions over this example of a proof by the contrapositive?
What does the square mean?
X squared is, x times x.
Oh, I meant the squared at the end of this.
That's where you end your
square.
proof.
Okay. Okay, I was a little worried that you were asking about squares.
He meant the square symbol.
Right. This is the symbol that represents the end of the proof.
Ah, gotcha.
You put it at the end of all your answers for proofs too.
Right. Yeah. So when you're finished, you should put a little symbol there to let whoever's reading it know that you're done. And that whatever comes after that isn't part of your proof. That's the idea.
Professor, mind if I ask a question that might help simplify it?
Sure.
How many of you people here go to a church where on the screen they have songs with the symbol at the end of it? That's kind of a way you can look at it this way.
Okay, yeah, I'm sure there are other cases, other places where you use a symbol to mark the end of something.
Yes, sometimes my church used to have either a red circle or red square nowadays at the end of the song to let us know they were coming to the end of it.
Okay. Yeah, so in your textbook, I think sometimes in this particular textbook, they use a triangle shape to mark the ends of things. Um, Other textbooks use filled in squares. And you could use any of these other symbols if you preferred. This is just the one that I like to use.
Sorry if that was a little disruptive, Professor.
That's fine. Okay, so let's move on to the third type of proof. And this is called proof by cases. And this is used when the domain of discourse, the things that you're talking about, can be naturally divided up. And depending on what your domain is, it could look different. So you might be dividing up into maybe positive and negative numbers if you're talking about real numbers. Or if you're talking about integers, maybe you want to split them up into odd and even integers because sometimes they behave differently depending on what you're doing. If you're talking about sets, a common thing is to talk about the empty sets and then talk about non-empty sets. So there's lots of ways that cases can work, and it kind of just depends on what particular thing you're talking about. And this example here is a fairly common way that cases can show up in a proof. This one is asking us to prove that for every real number x, x is less than or equal to its own absolute value. And we're going to use proof by cases. For this one, the reason that cases might come up is because we know absolute values work differently for negative numbers than they do for non-negative numbers. Remember, negative numbers we have to switch to positive, whereas positive numbers we don't have to do anything with. They don't change when we put an absolute value on them. So that's why we might need to talk about cases in this one. So let's just start writing. And maybe just let your reader know before you start writing your cases what you're going to do. So just say something like, we will use a proof by cases. And when I'm writing a proof by cases, I like to put essentially bullet points or headings. So I might come down to the next line and write case 1. And then I'll write whatever that case is. And then when I'm finished, I'll write case 2. And this just keeps things nice and organized for whoever's reading it. So like I said, this kind of breaks down into negative and non-negative numbers. So case 1, let's talk about the non-negative. So we assume in this case that our number x is greater than or equal to 0. And we know that if we take the absolute value of our number, we just get our number back. Remember, it's positive or non-negative. So the absolute value is the number itself. Since the absolute value of x is actually equal to x, we know that x is less than or equal to its absolute value because it's actually equal. Okay, so there wasn't really much to do here. Just writing down what was obvious, more or less. We do have to do slightly more work in case 2. So now we're going to assume that x is less than 0. So in this case, we know that the absolute value, we have to make it a positive number. And that means we have to put an extra minus sign on it. So in this case, we know that the absolute value of x is actually equal to negative x. So this might feel a little funny to put a negative on it when it's an absolute value, but remember we start with a negative number, so this minus sign makes it positive. Okay, so what's the relationship between x and the absolute value, if we know this? Well, let's go back here. We know that x is less than 0. So if I put a minus sign on both sides, we know that minus x, we have to flip the sign to the other direction. Minus x is actually greater than 0. So let's string this all together. We know we start with x that's less than 0. And we know that minus x is greater than 0. So we can continue our inequality. And minus x, remember, is equal to the absolute value. This means we can follow the string of inequalities in our equation here, equality, to see that x is less than the absolute value of x.
Your less than sign is backwards on the negative x. It's less than 0.
Here?
Yeah, isn't that supposed to be the other way around?
No, this is right. So since we started with x is less than 0, if we want to put a minus sign on both sides, so minus x and minus 0, which is still just 0, we have to change the direction.
Oh yeah, I remember that.
Yeah. So maybe we can just write a comment here that is x is less than its absolute value. And that's what we wanted. It's either less than or equal to. In this case, it's less than. Okay, are there any questions or any other questions over this proof by cases? Okay, so if there aren't any more questions, we can just keep moving along. to talk about proofs of equivalence. So in equivalence, this is related to if and only if statements. That's what we mean by equivalence. So remember, in logic, this was the biconditional. And the symbol for it was the arrow pointing both directions. And one thing we learned back in the last chapter is that the biconditional, the arrow, we should probably put in simple propositions there, P if and only if Q. This is actually logically equivalent to two separate conditional statements. So the double arrow breaks down into two single arrows. If P, then Q, and if Q, then P, like this. So we're going to use this fact that biconditionals break down into two pieces in order to construct our own proofs of equivalence. So this is something like a proof by cases, but the logic of it is just a little bit different. There's still going to be two pieces. Okay, so let's get right to the example. We want to prove that for every integer n is odd if and only if n minus 1 is even. So the keywords here are these, if and only if. That means this is going to be a biconditional. So that means instead of having one single part of our proof, we're going to have two parts. We need to break it down by assuming this, n is odd, and then showing that n minus 1 is even. And we also have to do the opposite. We need to start over here, assume that n minus 1 is even, and show that n itself is odd. Okay, so as always, start with the word proof, and then let the reader know what you're going to do. Let's start left to right. So we will start by showing that if n is odd, then n minus 1 is even. So in this first part of our proof, we need to assume that n is odd. So that means there's an integer k we're just using the definition of odd here. There's an integer k where n is equal to 2k plus 1. So how do we go from n to n minus 1? Well, we just subtract 1 from it, right? So n minus 1, we use this for n, 2k plus 1. And then we subtract 1, pointed to the wrong spot. We subtract 1. So we've substituted in for n. And when we subtract off the 1, all that we're left with is 2k. And that's what we needed. N minus 1 is equal to 2 times an integer. That means it's even. And that finishes off the first half. Are there any questions before we go the opposite direction?
Shouldn't we have stated what proof we're doing?
You mean state this whole thing, n is odd if and only if n minus 1 is even?
No, that we're doing proofs of equivalence.
Yeah, you could. It's not really necessary, I don't think. But if you want to, yeah. You could say something like, to show the equivalence, and then you might write this again. We will show, and then maybe finish that sentence off with the 2 halves. You could start your proof that way if you wanted. I just wanted to save myself some writing. Okay, so we finished the first half. Now we need to do the other one. So we need to start over here. Oops. If n minus 1 is even, then what we started with, n is odd. So now we're going to assume that n minus 1 is even. And remember, that means that there's an integer. And let's use a different symbol than we used before, something different than k. So there is an integer, maybe L. Such that n minus 1 is equal to 2 times L. And whenever you're using the letter L in math, it's important to use the cursive L instead of the print L, because usually there's no way to tell between a print L, a vertical line, and a 1, which is also a vertical line. So use the cursive little squiggle L. Okay, so what do we know? N is equal to n minus 1 plus 1 to cancel off that minus 1. But we know that n minus 1, if we group the n minus 1 together, that's equal to 2L. And then copy down the plus 1. So n is equal to 2L plus 1. And now we know it's odd, because it's 2 times an integer plus 1. And that's all we needed. If you wanted, you could have done something like adding 1 to both sides of this equation instead of writing it out this way. That would have worked as well. Are there any questions over this proof of equivalence? Okay, so since there aren't any questions, let's go ahead and move on to the last part here. Existence proofs. So far, I think in all of our proofs, we've been looking at universally quantified statements. So what we're going to look at in this kind of proof is the other kind. Let me just make a note here. So we've seen proofs with universal quantifiers, something like for every or for any. Those kinds of statements. These will work slightly differently, or quite a bit differently, really. And the most common way to prove a theorem of this form, existential, so there exists an x such that p of x, is just by exhibiting an example. So just writing something down where whatever this is works, where it's true. So another way of saying that is that we have to find a member, let's call it A, of the domain of discourse where P of A, when you plug it into whatever propositional function we're looking at, where P of A is true. So you just have to find a single example where this is true. And if we take a look at this example, it says let A and B be some real numbers where A is less than B. And we want to prove that there exists a real number x satisfying A is less than x is less than B. So x is somehow sandwiched in between the two numbers A and B. So we just have to find an example, a single example of a number in between A and B. One will work. So a single number x where this is true. So A is less than x, which is less than B. Can you think of any way that you know from maybe another math class, of finding one number in between two other numbers. Maybe a number exactly in the middle, the midpoint. Anyone remember?
Are you talking about the midpoint formula?
Right, the midpoint formula, and Victoria in the comments said that it's the same as the average. Yeah, that's right. The average of A and B in this case. So we can choose X to be the midpoint. So X would be A plus B over 2. And that's it. Well, maybe put a little box here. So you found the single point, the midpoint that's in between these two numbers. I need to silence my phone, apparently. Okay. Any questions? No? Okay. So the takeaway from this kind of proof, the existential proof, is that you just have to find a single example where whatever it is happens. That's all you have to do. So Nicholas is asking if we can assume values for A, X, and B. And the answer is actually no. Because in the problem, we want A and B to be any real numbers. If we specify numbers A and B, then it's possible that what we do wouldn't work all the time. So we have to leave A and B as variables in our answer. And if we're being super attentive to like the symbolic logic of what we're doing, this statement is actually this one. It says for all A and for all B, there exists an X where A is less than X is less than B. So this theorem is actually a triple nested quantifier kind of in disguise.
Would you be able to disprove that statement with a specific example, but you can't prove it, right?
Right. So if you can think of single numbers A and B where this doesn't work, then yeah, you could disprove it that way. That's right. Any other questions?
I'm looking back at number 4.
Okay.
What is L again?
It's just the letter L. We're using it. It's just the letter after K in the alphabet. It's the only reason. Here.
Yeah, so we pretty much just replace K with L.
Right.
Because we already used K in the previous example.
Right. We just don't want to use K more than once if we don't have to.
That's
That's
G.
the same way, like when you're writing computer code, you don't want to reuse the same variable name so that you don't break your program. So just pick different letters.
All right.
Okay, so that's actually the end of the section.